Last episode, we stood on giant shoulders. We took MobileNet V2 frozen and taught it to tell cats from dogs with a tiny head on top. But look at what it gave back, one label for the whole picture. Cat, that's it. The real world isn't that tidy. A single street photo has a person, 3 cars, a dog, a traffic light, all at once. So today we stay in the same pipeline stage, predict, but we go deeper into it. We make the output structured. Instead of one class, the model will hand us boxes around every object and then masks that label every single pixel. Where, not just what. Here's the thing classification quietly assumes one image, one answer. That worked for cats versus dogs because there was one animal in the frame. But hold up a busy street and ask, what is this? And the question breaks. There isn't a thing. There are many things scattered across the frame, each deserving its own answer. So the predict step gets richer. The output is no longer a single number or a single label. It's a list, and each item in the list carries a location. A box here, a box there, a mask painted over the road. Same stage of the pipeline, but the shape of what comes out has changed completely. Detection is really just two jobs stapled together. Classification, what is this? And localization, where exactly is it? Do those two jobs not once but over and over all across the image? Every object gets its own little classification plus where. That's detection in one sentence. And where is surprisingly simple to write down. A box is 4 numbers, top, left, bottom, right, or a center and a width and a height. The model doesn't draw a rectangle. It predicts 4 numbers and we draw the rectangle. It regresses the coordinates and alongside them scores how confident it is that something's really there. But the model can't try every possible rectangle. There are billions, so it cheats cleverly. It lays down a grid of candidate boxes ahead of time, anchors at fixed positions and sizes. Then its only job is to accept or reject each candidate and nudge the good ones to fit snugly. Pre-placed guesses, then yes or no, plus a small correction. That leaves a mess though. The same car gets caught by 5 overlapping anchors, so you get 5 boxes stacked on one car. We clean it up with non-max suppression, keep the highest scoring box, throw away every other box that overlaps it too much, repeat. 5 boxes collapse into one clean rectangle per object. Now turn the resolution all the way up. Forget boxes, label every pixel, that's segmentation, and the classic shape for it is UNet. The left side is an encoder. It shrinks the image down, squeezing it into a small, dense summary of what's here. The right side is a decoder. It grows that summary back up to full resolution, painting a label onto each pixel. But shrinking throws away fine detail, exactly the detail you need to trace a sharp edge. So UNet adds skip connections. It hands each encoder layer's fine-grained map directly across to the matching decoder layer. The decoder gets both the what from below and the where from the side. That's how the edges stay crisp. And once you can read individual pixels this precisely, you can do something wild. Pixels can even hide text. Next time, we'll read it. OCR. 2 pages of code. Page 1, load a pre-trained detector, run it on a street photo and draw the boxes. Page 2, build a small UNet with the functional API and overlay a semantic mask. No training today, both are about the predict stage, structured output. Let's walk it. Up top, imports and the image. We pull in Keras hub, that's where the pre-trained vision models live now, plus matplotlib for drawing. We load a single street photo, resize it to 800 by 800, the size this detector was fine-tuned on, and add a batch dimension, one image in, a batch of 1. Now the model, Keras hub models image object detector from preset with the retina net, ResNet 50 FPN preset, pulls down weights pre-trained on Coco, 80 everyday classes, person, car, dog, traffic light all in there, one line, And we have a detector that's already seen millions of objects. We call model.predict on the batch and get back a dictionary, boxes, confidence, and labels, each padded out to a fixed number of slots. Real detectors always pad. Most of those slots are empty. So we filter, keep only the detections whose confidence clears the threshold, say 1/2. The non-max suppression we talked about is already done inside the model. This threshold is the last cut. Here we turn label numbers into words with a small Coco name map and print the survivors. This is the terminal line you'll see: person, car, dog, each with its score. Exactly the structured output, a list, each item carrying a class and a location. One thing to know, these boxes come back in x6 order. P1, x1, y2, x2. We'll respect that when we draw. And we draw. For each surviving detection, we unpack its 4 numbers in x6 order, then add a matplotlib rectangle from the top left corner with the right width and height, gold for people, magenta for vehicles, and write the label above it. That's the left panel of the figure, the street photo, boxed and named. Page 2, segmentation. We build UNet with the functional API. The encoder is 2 conv plus pool blocks that shrink the image, and remember each stage is feature map. Notice we keep C1 and C2. Those are the skip tensors we'll hand back later. And the bottleneck is the squeezed middle, the densest summary. Then the decoder upsamples back up, and at each step we concatenate the skip tensor from the encoder before the next conv. That concatenate is the skip connection. Fine detail from the left, meaning from below, joined. The final layer is a 1x1 convolution with softmax over the classes: background, road, sky, person. That gives a class probability for every pixel. We resize the same photo to UNet's input, run it, and argmax across the channel axis to pick the winning class per pixel. That's our mask. We tint it and overlay it on the photo. The right panel, road in one color, sky in another, people in a third. 2 pages, 2 kinds of structured output, both living in predict. Next time we zoom into the pixels far enough to read the letters hiding in them. OCR with a CNN, an RNN, and a CTC loss. See you there.